Hello, good morning, and thank you for being here. It's my first time at Build Stuff, so thank you for having me as a speaker. So this topic, REST versus GraphQL versus gRPC, it is such an evergreen topic. Years and years pass by, but I don't think the debates, the discussions, the conversations between team members just don't change. But what actually get lost sometimes in that debate and conversation is the basics of these three API paradigms. It is such three different API paradigms that a comprehensive comparison is required, and the use cases are also quite different when it comes to these three API paradigms. So I hope to have a conversation about the basics of these three API paradigms, and then we can finish off with what I think is a comprehensive comparison and potentially the use cases of all these three API paradigms. A little bit about myself. I am Poornima Nayar. I'm a freelance .NET developer, and I live in Berkshire, UK. I'm a Microsoft MVP for developer technologies, and I'm also an Umbraco MVP. For those who don't know what Umbraco is a .NET-based open source CMS, and I'm quite an active community member there too. Non-work me, I'm a mother. I have a beautiful 9-year-old who is currently at home with Daddy Dearest. And I read a lot. I'm also a student of Carnatic music, which is a stream of Indian classical music. I've been training for the past 5-6 years in Carnatic music. And that's my Twitter handle, should you wish to connect with me, or handle on X. I'm also on Mastodon using the same handle. You'll find me on the .NET.social server. So straight into the topic, let's talk about gRPC. gRPC is a modern, open source, high-performance remote procedure call framework. So it's a flavor of remote procedure call framework. gRPC, as much as it is kind of newish, RPC is not. RPC has been out for some time, 1970s or 1980s. In fact, if you go back to .NET Framework realm, WCF was your choice of RPC, or the flavor of RPC framework that you had in .NET Framework. But these days, it's gRPC. But before we move ahead, let us actually look at what a RPC, or remote procedure call, is. Wikipedia tells me that remote procedure call is when a computer program causes a procedure to execute in another address space, commonly another computer, which is coded as if it were a normal procedure call, without the programmer explicitly coding the details for remote interaction. A very, very, very long sentence, but let us just try and break down the gist of it. The word procedure kind of shouts out at you at many, many different points. So procedure is a key word here. The second one is there is a program, that is my client app, which communicates or which invokes a function, but in reality, that function call actually gets executed on the server. So there's a network jump happening. So location transparency, that is one of the key features of any RPC framework, and gRPC does the same. So let us have a look at how program flow works with a gRPC client-server architecture. We have the client functions, which invokes a client stub. A stub is nothing but a representative of the server function that it is trying to invoke. The client stub packs the parameters using a process called marshalling. It passes on the control to the RPC runtime on the client, which forwards that to the RPC runtime on the server, invokes the server stub where the parameters are unpacked, and it actually calls the server functions and executes the server functions. So my client stub, or the method invocation, happens here, but the execution happens here. So the location transparency is one of the key features. The client doesn't actually know that it is invoking and running the function on the server. For it, it looks like a local method is being invoked. And once the server function executes, the response comes back to my client function the way it went in. So with any RPC framework, be it gRPC, procedures or methods or subroutines, they are the key or the star of the show. Invoking a function in another address space, but invoking it as though it was a local function. That is the gist of any RPC framework. Specifics about gRPC, it is Google's implementation of RPC. It was initially called Project Stubby and was made open source and called gRPC in March 2015. I am a .NET developer, so there will be some .NET coming into this talk today. but there won't be any code. Whatever I speak today can be applied to any programming language, REST, gRPC, and GraphQL across any programming language. But talking about gRPC in .NET, we have official support for gRPC from .NET Core 3.0 onwards. In fact, these days, if you're looking at RPC requirements for your project in the .NET realm, gRPC is the favored framework. gRPC favors contract-based API development, and it is designed for HTTP too. So you have a contract which is defined in some format, and to implement your service, you make use of that contract. So you are kind of adhering to a blueprint there. With gRPC, there's support for a lot of programming languages out of the box. And this makes gRPC a good candidate for polyglot systems. We'll talk about that more as we go on. The key term to understand with gRPC is protocol buffers. You cannot talk about gRPC without talking about protocol buffers or protobufs, because they are the open source mechanism to serialize structured data. Think of JSON, but smaller, faster, and performant. That is protobuf for you. But protobuf is a very wide term. I have put it down as interface definition language, so your contract is defined using protocol buffers and message exchange format. But if you look at the protobuf website from Google, it talks about protobuf as interface definition language, message exchange format, and even beyond. Jumping the gun a bit here, there's always code generation happening with gRPC. So even the code generated, the intermediate code generated, that is also a part of protobuf. But for simplicity's sake, let us talk about protobuf as our interface definition language and message exchange format. It is language neutral, platform neutral, and extensible. It is forward compatible and backward compatible, so it is incredibly smart. This is another reason why gRPC is very good for polyglot systems. And talking about requests and responses with protocol buffers, they are in the form of what is called as messages. So this is an example of a message. This looks like a response that comes back from a method in my service. So each message is a record of key value pairs where each field has a type and a number and a name, obviously. These messages, when they are transmitted in binary format. So it is small in size, of course. And when this message is serialized and deserialized, the value is actually stored against this number rather than this name of the field here. So that again reduces the size of the messages. Another thing to note with protocol buffers is that with any field in protocol buffers, there's no concept of null. So if you don't assign a field value to the first name, when it is transmitted, it is assigned the default value for that particular type, so in this case, string. So if it is not set, it is just not used. And there is no concept of null with protocol buffers and messages. So that, again, in turn, reduces the size of messages with protocol buffers, which is why it is smaller, faster, and performant combined with the binary format. And we spoke about the contract of the API, and that is all defined in what is known as protofiles, which are files with .proto extension. But they have a certain decorum, a certain syntax, and that is where you have the contract of the API, the definition of the gRPC service. Typically, one protofile means one service. And within each service, you can have as many procedures as you want, or in this case, they are called RPC definitions. And of course, you can also have messages sent between the client and the server as a part of the protofile. This is at the simplest form. You can split out the message into another protofile if you need to, but that is more advanced or something that I would speak in a kind of niche gRPC talk. So this is how a protofile looks like. I've taken this out of the Visual Studio out-of-the-box template. It starts with the syntax, which is Proto 3 at the moment. This is the syntax for protobuf. This is quite proprietary. Then we have some options for code generation. We have a service definition here. So I just have a single service definition called greeter, and I have a single RPC definition called say hello. But in reality, you might have many, many such RPC definitions. Things to note here, it is a single request and a single reply. So the request and reply can be seen as like an encapsulated object, but with many, many fields. But it can only be one request and one reply. It cannot be hello request and something else. It always has to be one single thing, unless and until you are using streaming. So this is your proto file, and this is where your proto-C compiler kicks in. So across various different programming languages, proto-C has the understanding of how to generate code for a particular language. So in .NET realm with C#, proto-C compiler knows how to generate the code following C# conventions, and the tooling kicks in to generate code for me. And the proto-C compiler can generate both server-side and client-side code. Server-side code is for implementation of the service, and for any client to consume a gRPC service, it also needs client-side code generated, because that is where your client stubs live. So sharing of the proto files is quite necessary there. But because it's proto-C compiler, which can understand many languages, I can easily write a .NET-based service, which can be consumed by a Kotlin client, because I'm sharing the proto file, and the proto-C compiler helps me generate the client-side code. The server-side code that it generates acts as the starting point to implement the service. So in .NET realm, I get an abstract class with virtual methods, which I can then override to give my own implementations. And the client-side code contains the stub methods to invoke and execute my service methods. So that is the gist of gRPC. Now, if suppose I have a user database, and I want to perform CRUD operations on it, what would my service look like? So I'll have a service called user service, and I would have my many method or RPC definitions: get user, get me a particular user, create, update, delete user. So it's very action oriented. Do this, do that. It's just doing things. That is the gist of RPC. Now, what if we have to extend that user database, say, to a fictitious social media platform, where each user has, say, comments, stories, you want to get the top activity of a particular user? Again, you would fill up your service with many, many RPC definitions, probably in a second proto file, to achieve that. So it's very action-oriented. For anything and everything that you need, you start off with RPC definitions and implementing them. So that is the gist of gRPC and how you would lay out your RPC definitions, and a little introduction on how you would create a gRPC service. I'm not going to code at this point because I think that is quite an overkill for my talk today. But let us talk about the pros and cons of gRPC. With gRPC, we have lightweight messages, we have high performance, and we have reduced network usage with protobuf, with it being in binary format. There's code generation supported for a variety of languages, which makes gRPC a good candidate for protobufs, polyglot systems. And if you have streaming requirements in your project, streaming options are a possible choice with gRPC. It makes use of the HTTP2 multiplexing and streaming capabilities quite efficiently. So you can have further 3 modes of gRPC called client streaming, server streaming, and bidirectional streaming. And of course, gRPC is scalable. But being a contract-based API, there is always some coupling between the client and the server. As of now, we have limited support in browsers or browser-based apps for gRPC. The reason being, the low-level browser APIs cannot actually work very well with the gRPC client. So if you're looking at web apps, Blazor apps, potentially not a choice for gRPC. It is suited for microservice to microservice communication. Of course, it is an API, so we need our contracts to be discoverable. At this point, what you have is a proto file. So you have to have comments in your proto file, and that needs to be shared with your clients. And you need to seek third-party tools to actually make your contract blow into like beautiful websites like what we have with Redoc or Elements. And what can be the key star or the star of the show with gRPC, that is function. It can actually go against itself as well, because it can lead to function explosion. It can just build up. And of course, debugging can be a little bit of a pain, because our messages are not in a human readable format, it is in binary format. But again, there are tools to overcome that. And that brings us to REST API, which is the most widely adopted API paradigm potentially in the world, to the point it's been used, abused, and misused. I prepared for this talk like 2 years ago for the first time, and I think every notion I had about REST API was broken when I did the preparation, because more than often, what we speak about REST API and what we actually do with REST API are two very different things. Every time I've given this talk, I've learned something new about REST API. But let us talk in detail. REST stands for Representational State Transfer, and it was first presented by Roy Fielding in his famous dissertation in 2000, where he suggested REST as an architectural style for distributed hypermedia systems like the web. So REST was put in place to standardize web. It is not a specification, it is far from a specification, it is just guidelines on how a RESTful system can be, and it leaves the implementation to you. With REST, we are thinking in terms of resources. Anything that can have a computer-readable format can be a resource. You and me, this talk, a pomegranate, anything can be a resource. So REST says, here is a resource, here is what you can do with the resource. Here's a collection of resources, model them. That is what REST is. Everything is in terms of resources and related resources. Every resource has a unique resource identifier. And with REST, you are using representations or resource representations between the client and the server. This is just one of the representations. This is not what REST tells me to use. Because we are talking API and JSON seems to be the preferred format, I have put it down as JSON. But a resource representation is typically data that you see up there, some metadata that is in the form of headers in this example, and some hypermedia links. It need not be links, it can be text, can be imagery, but I've stuck to link because that is probably well suited for the situation. REST doesn't tell me that this is the representation that you should have. This is just me saying that this is a resource representation. Now, what is the gist of REST? Representational state transfer. You have the resource representation that is stored on the server, the resource state, and you have the application state stored on the client. So when the client wants to change the resource state on the server, the client sends in a resource representation to the server. And when the application state on the client needs to be changed, the server sends a resource representation to the client. So transferring the state using resource representations is the gist of REST, representational state transfer. And with REST, we have these 6 constraints, or the Roy Fielding constraints. Anything that adheres to these 6 constraints can be considered a RESTful system. Not just APIs, not just web, any system. So the first one is client-server, which means that you have a client, you have a server. The client asks for information, the server gives you the information back in an uninterrupted manner. Things should be stateless, which means that any request from the client should hit the server, and the server must be able to provide a response without it being dependent on a request that came before it or after it, which means that session state goes in intermediaries or in the client, no session state on the server. It should be cacheable, which means that any request from the client can be processed by the server, and then the response sent back. And that response can be cached at the intermediaries so that it can be then used as response for further equivalent requests. Then you have layered systems, which means that any RESTful system can be made up of layers, where each layer talks to one above it and one below it. And layers can be added, changed, or even taken away without affecting the system. Code on demand is an optional constraint, which says that even executables can be served as a part of your RESTful system. The final one is the uniform interface, which is the most important REST constraint, and it is subdivided into 4 different sub-constraints. Identification of resources, which means that every resource has a unique way of identifying it. You can manipulate resource through resource representations, like I explained, and that representation can be anything: JSON, XML, text, imagery, anything. You have self-descriptive messages, which means that each message should be complete in itself for the server to take action. And then you have HATEOAS, which is hypermedia as the engine of application state, which we will touch upon, but HATEOAS is the factor that completes REST. If you want a completely decoupled client and server, your server should opt into HATEOAS, and the client should actually use what you send in as a response using HATEOAS as well. Without it, you cannot have a completely decoupled system in REST. Some of the myths about REST is that every time you serve JSON over HTTP, that is REST. That is so not the case. Just because you serve JSON over HTTP, that doesn't mean anything about REST. I can serve JSON over HTTP. Did we speak about JSON or XML in the REST constraints? No. Did we speak about HTTP in REST constraints? No. So anytime and every time you just say that I will write an API that serves up a JSON and that'll be a REST API, just think to yourself, it's not REST, or say to yourself, it's not REST. And just because you invoke a procedure, say over HTTP, I'm talking about APIs and HTTP here. So just because you invoke a method, say using HTTP, that doesn't mean REST either. That is RESTful procedure calls. It's not REST. And REST is not HTTP either. REST is an architectural style for distributed hypermedia systems like the web that still runs on HTTP. And HTTP is a protocol. So you have similarities between the two because Roy Fielding was involved in REST. He was involved in HTTP. And he saw REST as a way of standardizing web that runs over HTTP. So there are similarities, and that's where it ends. But what REST does is it reuses HTTP. Whenever we have a REST API that functions over HTTP, we reuse the toolkit that HTTP provides us. That is the HTTP verbs, requests, responses, the headers, the status codes, all of that. So thinking about the same user database, how would I have my APIs laid out? So my resource is user. So it starts with a unique URL for my resource, that is /users. I would issue the various HTTP verbs depending upon the scenarios that I have. If I want to create a user, I would use the post. Put or even patch can be used to update users. Then I would use the delete verb to delete user. And of course, to read user information, I would use the get HTTP verb. And depending upon the scenario that I have and the HTTP verb in place, I might have a request body, and I might have a response body, and an appropriate status code is expected in each scenario. So that is REST or HTTP API on the user database. But what if you want to extend this user database in the case like before, where you have stories by users, where you have, say, comments for stories, when you want to get top activity by user? Should you be writing methods and then invoking them using HTTP? No, that would be RESTful procedure calls, and that's not what REST asks us to do. And that is where HATEOAS kicks in. This is often said as the REST nirvana. When you have HATEOAS is when you have the glory of REST. HATEOAS is the acronym for Hypermedia as the Engine of Application State. So what we saw in the previous slides, using the HTTP verbs and users stick to the HTTP API, where you're thinking about resources as well as HTTP verbs. So think about a website which you're browsing, say to the home page. You hit the server sends you back the data of the home page, and it also tells you what more actions you can take. Maybe you can say go to the blog page, maybe you can say go to the About Us page. So that what next, what more can you do with this particular resource, that information is given to you by the server. And the application state that is on the client, you achieve a new application state. That is, you go to another page, say About Us page, based on the data that you get from the server rather than it being hard-coded on the client. So changing the application state on the client using what hypermedia or what options the server gives you, that is hypermedia as the engine of application state, or HATEOAS. So simply putting it, hypermedia to drive the changes in application state is HATEOAS. So to make things further more clear, any response that I get back from the server, this could be a representation of it. I have the data corresponding to a user ID called 1, Harry Potter, and I have some information as a client as to what more actions can I perform with this particular resource. I could get the resource, I could update the resource, I could get the related resources as well related to Harry Potter. So all such related information is provided to me by the server rather than me kind of hard coding or looking for it. And I, as a client, I'm supposed to use this to achieve the next application state. I don't need to know that information beforehand. So HATEOAS is more like, hey, you do not need documentation for your API or whatever it is. I am the documentation. Use me, and that will provide you a completely decoupled client and server architecture. But as much as this is the reality, I think this looks weird. But personally speaking, I think that comes in from the factor that REST was put into standardized web, which runs on HTTP, and we are bringing that RESTful paradigm down to APIs and trying to fudge fit in something like this to help the clients out. Now, as much as you give this to your end users, unless and until they use this, you cannot have a decoupled system in REST. Now, moving on, something more about the HATEOAS Richardson maturity model, which was put together by Leonard Richardson. He sees hypermedia controls in the response as the glory of REST. So this is the maturity model, and there's a link to the article that I've provided as well. It is a great read. I think you should go and have a read at it. So level 0 is where you have the swamp of box, plain old XML. Level 1, you start thinking about resources, but you still don't use the HTTP verbs. Level 2, you start thinking about HTTP verbs as well as resources, and I think this is where most of the real-world APIs live. And level 3, where you have hypermedia controls in your API response, that is when you have the glory of REST. Currently, I don't think there's a standard for implementing hypermedia links. Everyone does it their own way. And I think application HAL XML and HAL JSON are kind of the work in progress MIME types. So what you would have with a REST API ideally is a root entry point and something like this where the client can actually browse through. So I am kind of mimicking this using a button, a mouse click, but a client is actually supposed to browse through your API like this. This is how REST APIs should be when it adheres to the REST constraints. Now, talking about the pros and cons, we have decoupled client and server again with REST API, as long as you have HATEOAS and the client uses those hypermedia links. And if you have achieved that state, your API can evolve over time. REST APIs are always scalable. There's seamless integration and reuse of HTTP, which means that it is easy to consume. Literally any client that can issue an HTTP request can consume an HTTP or REST API. And of course, there's superior browser support for everything that runs on the web. I think REST or at least HTTP API is kind of a default choice. But where it lacks is it can become chatty. So when you have truly RESTful systems, you do not have procedures. You are bound to go, say, users, stories, and work out in a long-winded way on how to gather the information that you actually need. So it can get really chatty, which means there's overfetching. That is, I fetch a lot of data, a lot more than I need, and then disregard what I don't need. It also means underfetching, which means that at no point do I have everything that I need to, say, fulfill my purpose. So I go after fetching more and more data. So overfetching and underfetching goes hand in hand. And of course, there's the N+1 problem on the client. And it, of course, leads to big payloads. And finally, there's no single spec. Across the world, developers have come across with best practices and practices that they follow, which we all follow as a community. And the chattiness, the overfetching, underfetching, and N+1 problem on the client is what led to GraphQL being in very existence. I'm not going to go through the history of GraphQL for a minute. Let me have some water. But just understand that it is the downsides of REST which led Facebook engineers to rethink their API approach and came up with something very fluid, which is GraphQL. Now, GraphQL is very different because GraphQL is actually a query language for your API. It is not actually an API. But what you have typically with GraphQL, provided you are working with HTTP, is a single smart endpoint which takes in your queries and then builds the data output for you. So it's very fluid. Depending upon what your query is, the response changes as well. So it's very client-focused. So in this example, I am asking for a course with ID 1045. I have some information that I'm asking about the course, and I'm also asking some related information about the course. So typically, course and enrollments are, or might be two different entities, but with GraphQL, I have a way to query them all in a single shot. And what I get back is quite surprising and quite amazing because my response, which is in JSON, is a mirror image of my query. If you look at it, it is predictable. So I, as a consuming developer, knows what to expect. Furthermore, if I have asked for something, that is exactly what I get. I don't get everything, or I don't get anything more than I asked for, so it's pretty green. And with GraphQL, there is no way you can say, I have a course entity, get me everything. No, that is not possible. With GraphQL, you have to say, for a course, I want all this information, and that's exactly what GraphQL will fetch for you. So GraphQL is like that smart person that stands between you and data that says, hey, tell me what you want, where you want it from. I'll make that happen for you. So just reiterating what we just saw, clients control the shape of the data that they need. I could be asking something else in my query, and that is exactly what the server fetches for me. The server responds back with the exact same data graph in the same shape that I asked for, and it only responds with what has been asked for, nothing more and nothing less. So the star of my show here is queries. Because I'm in control, I ask for what I want, I get what I ask for. That is it. So it is unashamedly about being that client-focused, experience-driven API. That is what GraphQL is all about. And where does GraphQL get its name? Because when you have entities, GraphQL is good at understanding the relationship between your entities and forming that hierarchy and visualizing it as a data graph. And then it tries or helps you to extract parts of that data graph. That is where GraphQL gets its name from. Now, how does the server understand your queries? That is because on the server side, there's usually a runtime which kind of understands your queries, parses it, validates it, and executes it for you. Now, you don't have to do much about it because how that runtime should be implemented is a specification, and you do not have to go ahead and implement a server or a runtime yourself either, because there are a lot of implementations of GraphQL across various different programming languages and platforms which sticks to the specification. So all you have to do is specify your types and fields, and the platform will do the rest for you. So as I said, various implementations. If you're looking at something in .NET, I know of Hot Chocolate as well as GraphQL.NET, which can help you achieve or implement a GraphQL server. One key thing to understand with GraphQL is that it is an application layer, not an API in itself. So it stands between you and your data. It can be, your data can be in a database, it can be a REST API, it can be a GraphQL server, it can act as a gateway, but GraphQL is an application layer. So sometimes GraphQL is also called a GraphQL server rather than a GraphQL API. And at the heart of any GraphQL system, server, is a strongly typed system called the schema, which is what your queries are validated and executed against. This is all about the shape of your data, not where your data is stored. And schema is made up of types, starting with object types, which is a representation of the object. Queries, which are meant to read data. So queries are the root operation type to read data. Then you have mutations, which are root operation types to insert, update, or delete data. And then you have subscriptions, which stands for pushed updates from the server. So that is your object type. So users, comments, stories, that is my object type. And these three are the root operation types for any GraphQL system. So with object types and queries alone, you can have a GraphQL server in place. You don't need mutations and subscriptions to have a GraphQL server. The minimum requirement is these two, queries and object types. And all of this comprises the types, and that is a key thing to understand. Be it object types or the operation types, they are all types in GraphQL. And each type is made up of field, with each field having a name, a type, and resolvers, which help you resolve your field into concrete data. Now, let us talk about the types and the fields. So if you think about the user ID, name can be fields. If you talk about story, the ID, the story title, headline, all of it can be fields. But when it comes to queries and mutations, that is when it gets interesting, because they are also types. So starting with queries, in my user database, I can have options to read a list of users or a particular user using these two fields. When it comes to mutation, I can have fields for creating, updating, or deleting users. And subscription, which kind of works in conjunction with mutation. For example, when a user is created, maybe I want to send an update to all subscribed clients. So I can have a field to send such updates when a user is added, or maybe when a user is updated, or maybe when a user is deleted. So this actually kind of is your API. You have your object types, and then you have your fields, which actually help you translate or get the information that you want. And the GraphQL queries that I would issue to communicate or help me do my job can look like this. So that is for getting all users, getting a single user, getting the mutations, that is to create, update, and delete, and a subscription. This is very abstract, I know, but within the 10 minutes, this is the maximum I think I can do without code at this point. It is a very vast topic. Trust me, to get to the basics of GraphQL, it took me time to wrap my head around it. And if I want to get related information, that is a user, the story, and the comments, I can do something like this with my query. I don't need to do anything in the backend, because the minute I have my entities laid out and the relationships kind of laid out, using the programming paradigms that I know of, GraphQL works out the hierarchy and helps you achieve something like this. So I can expect an answer for this from my server. So the pros and cons of GraphQL, we are dealing with exact fetching. We get what we ask for, nothing more and nothing less. We have a loosely coupled client and server. And typically, GraphQL servers are set to be version free because the client is always in control, and often versioning is not needed because of that. And GraphQL has this cool feature called schema introspection, which means that it can query itself to learn more about itself. And that has led to many IDEs and tools like Banana Cake Pop, Insomnia, GraphQL Playground, which can actually gather the information from your code and present some kind of documentation as a starting point to the developers. And of course, you can use third-party tools to kind of come up with full-blown documentation on top of that. And when it comes to the cons, there you have the caching complexity. When you're using GraphQL over HTTP, even reading information is over an HTTP post. So that is not quite cacheable. So the ways to get around with is persisted queries, where you have the queries cached against a unique identifier and then the data fetched. You can have performance issues with complex queries when you start nesting many levels below. You have a learning curve. I think the steepest learning curve I encountered was with GraphQL, because the concept is so different from REST and gRPC. And it is a growing community. There are giants who use GraphQL, but it's still a growing community wherever you go. Many developers start as consumers of GraphQL rather than someone who implements a GraphQL server. Now, talking about how they compare, I have 5 minutes. So let's go quickly through the comparison. The fundamental unit of REST is resources. With GraphQL, it is queries, and gRPC is functions or procedures or RPC definitions. The coupling is very low in REST, provided you have HATEOAS and client uses HATEOAS. GraphQL, again, is low coupling. gRPC can be high because it is a contract-based API. Chattiness is the highest with REST, as we saw, and low with GraphQL and gRPC. Caching, HTTP caching is made use of by REST APIs. GraphQL, we need custom caching. gRPC, I have come across one video that talks about Redis caching. I haven't come across it more than that because underneath the hood, if you're using gRPC with HTTP2, it uses HTTP post for everything. Discoverability is bad with gRPC because it's just a proto file as your contract. With REST, if you have HATEOAS, and of course, if you're sticking to HTTP APIs, you have Swagger these days for documentation. And of course, GraphQL, it is introspective, so it can help you with a good starting point. Versioning can be needed with REST. Typically, GraphQL doesn't need versioning. With gRPC, again, you need versioning. But gRPC, let me just put it simply that there are things in gRPC which can help you version even at a later date, even if versioning is an afterthought. And it can be done quite seamlessly as well. When it comes to statefulness, REST has to be stateless. GraphQL with queries and mutations are stateless, but with subscriptions, it's a long-standing connection between the client and the server, typically using WebSockets, so it's stateful. With gRPC, what we saw today was the unary mode, which is stateless. But when it comes to streaming, client streaming, server streaming, or bidirectional streaming, because HTTP2 has kind of a stateful nature there, it can be considered stateful. Performance is good with REST. It can suffer on complex queries with GraphQL, and gRPC is very performant. Payload size is the lightest on gRPC, and with REST, it can be quite heavy. GraphQL, it depends upon what your query is. The payload format typically is JSON with REST because we are talking about APIs, but REST doesn't say anything about the payload format as such. GraphQL, it actually mentions JSON in its specification, so we can go with JSON there. gRPC is binary. Browser support, GraphQL and REST are fine, but if you're thinking of browser-based apps for gRPC, gRPC Web, or gRPC JSON transcoding, which adds a layer of HTTP APIs on top of your gRPC API, is the only choice there. As far as being a standard is concerned, REST is only best practices. The other two are specifications. REST is the most mature out of the three. The learning curve is highest on GraphQL compared to medium on the other two. Learning resources, REST being mature benefits from maximum resources. And again, because I'm a .NET developer, something about .NET support, REST and gRPC have out-of-the-box Visual Studio templates. But if you're thinking about HATEOAS, there is no standard even in .NET. GraphQL, it is third-party implementations. Again, Visual Studio, we have out-of-the-box templates with REST and gRPC. And when it comes to hosting, REST can be hosted on servers, app servers, Azure Functions, container apps. GraphQL, again, the same choices. But gRPC, we are kind of limited in the Azure realm. You have to stick to Kubernetes. Container apps works like a charm. Azure App Service, if you're using Linux plan, it works like a charm. I have use cases very quickly. REST for management APIs, where the focus is on resources, varied client usage, microservices. GraphQL, when you have mobile apps, because that is the reason why GraphQL came into existence. When data needs fetching from multiple APIs, like a gateway, that is again useful. gRPC, all these are the use cases, action-oriented APIs, polyglot environments, microservice to microservice communication, IoT, internal services within the organizations, all can benefit from gRPC. I have put together a huge list of resources for you, and I've kind of put together my talk for the day as blog post as well. I have done this talk previously as a 1-hour version, so I've got a link to that as well, where I've got slightly more information. That is everything put together. Thank you for having me today. If you have the time for questions, I can take them now, but I'll be around at the conference later on as well if you want to come speak to me. Thank you very much.
Thank you so much. Does anyone have a question? Yes, in the back. I'll come to you.
Thank you very much. It's actually a question from the online chat. It's concerning REST APIs. But the application still needs to know where is update user that you can do and what it means. So don't you need a documentation and to know what object to send, where, etc., which is the reason why HATEOAS isn't really used anywhere, right?
Absolutely, absolutely. HATEOAS is just what completes REST APIs as completely RESTful. This is where I said things get weird as well. HATEOAS, when you look from the web perspective or say website perspective, is perfect. You are being sent back a list of links on what more you can do. But with APIs, you cannot really do that. So when I'm talking about pure REST, I have to put that in. But in reality, this is where I said nearly most of the real-world APIs are HTTP APIs combined with Swagger or OpenAPI, which gives you a more real-world kind of documentation. And then, of course, you have something like Elements or Redoc, which can provide documentation as such more than exposing your API contracts. Does that help? I'll just go with that helps.
All right, we have one more question, so I'll come up to you.
The questions are always about REST. I don't get anything about gRPC or GraphQL.
This one is from about gRPC.
Yeah.
If we were to implement authentication on the application side, does gRPC support and how?
Yeah,
at
absolutely.
which step would it happen?
So I'm a .NET. So are you talking about the stack?
No. You presented the flow of gRPC call.
Yeah.
Like, at which step of that flow would you authenticate that you can proceed?
So I can talk from a .NET perspective because I'm a .NET developer. So when it comes to gRPC is nothing more than a middleware in .NET. So you can use that middleware in conjunction with any authentication or authorization middleware that you have in your .NET stack. So that would happen at the RPC runtime level or just before it, because you need authentication before it gets to the server level. And of course, you need such information sent from the client as well. So when you're sending the information or when you're invoking the API on the client side, you need the access token sent in from there too. Yeah, does that help?